Good afternoon. I'm Salim.
And I'm Carlos.
We're SRE from Google, and we're here this afternoon to talk about lessons we've learned when productionizing machine learning services. And these lessons draw on conversations and experiences we've had with groups across Google and beyond. And I want to emphasize that we're not data scientists, and we're certainly not machine learning ninjas, but we are SRE, and we have a lot of natural curiosity. So a little while ago, when Carlos began building an ML pipeline, we wondered, how do we get this to production? How do we make sure it's reliable? And what happens when things go wrong?
So in order to start, let's try to show a bunch of things that you probably heard about machine learning and try to find the mistakes. I've heard machine learning is easy. I don't think so. I heard machine learning is the new thing. I don't think so. Machine learning is a black box, and you don't need to know more. Just different opinions in here. You train once, and you're done. Not at all. You rarely roll back. BS. Machine learning monitoring is like any other monitoring. No. More data is better. I'm comfortable saying that. I hear many data scientists telling me more data. You will learn all the patterns. I don't believe so. Otherwise, you go into overfitting. Your model is just a specific small things. It's transparent to the user. You will see that that's a lie. And compatibility is a knob. If you've used, for example, TensorFlow, the API keeps changing. So what is machine learning good for?
It's good for everything. Well, almost everything. We found that it's not good if you don't have a fallback plan. We'll talk about what fallback plan really might mean. It's not good if you don't have enough labeled data. And in particular, if the enough means that your data doesn't have the right quality or right uniformity to lead to a good model. And ML is not great if whatever application you're building or whatever service you're providing requires microsecond latency. And heuristic-based models still outperform ML. The lower bound for ML model-based services that we encountered was around 1 millisecond.
So in here, we're basically showing some of the use cases of machine learning currently at Google. You might be familiar with some of them. Ads. The ads team is basically trying to predict how many clicks they're going to get on some of the ads. Prefetching. There's teams using prefetching in memory addresses and file accesses. We use machine learning for resources and scheduling. We basically have machine learning models that learn how much CPU and RAM we are using, so it helps us to do capacity planning. We also use them for speech and translate. OK, Google allows to identify a speaker. It identifies the language. Sometimes it does a good job in translations, for example. We use it a lot in fraud for credit card detections, for credit card transactions, bad detections. You might have seen Gmail. It uses machine learning for the smile replies, very useful small boxes that you can easily respond to an email. And you would see it in the area of perception, Google Photos, detecting people, tagging people, or in YouTube with videos. But let's talk specifically about one machine learning model that is very important to Google. And that one is basically YouTube What's Next. So what I did in this screenshot is basically a search for SRE 2018, and I got a bunch of videos. Most of the videos that I got on my left side are technical talks. However, there's some suspicious over there, which is the second one. I'm not sure if you're able to see it, but it's basically a soccer match. I'm from Spain. Yeah, soccer is usually the sport that we like. One thing that this model shows you is that you need continuously training because you want viral videos that are continuously being watched by people to be easily disseminated. So those videos are probably going to be out there. You want to keep high accuracy. Keep high accuracy by having worldwide data. Videos that are famous 1 hour in Asia, you want them to also be available in Europe. The more time people are watching the videos, the more revenues we'll get because we get advertisement on those videos. You may see in the presentation that we will talk about special events one day. So for example, we'll talk about what happens in New Year's Eve or the Super Bowl. Those are days that your data, if you use that data for training, you might get some bias. Because it's a specific day where everybody is just celebrating one thing or getting very, very crazy about football. That might not be useful for other days. You will also see that the user can easily detect sometimes that the model is not acting correctly. If that second video, instead of being soccer, was wrestling or boxing, I would say, that doesn't belong to me. And you would see also that there are several machine learning models that can and cannot have a fallback mechanism. In here, if we didn't have this machine learning model, I could show you what is everybody watching in the wall, and I could say that's a machine learning model, okay? But if I have a machine learning model that is doing a translation, for example, from Spanish to English, and it fails, I have to stop that application feature in my website immediately. However, putting this in production is not easy. You have to guarantee freshness. That video that I was telling you that it becomes vital. You have to be taking into account multiple devices. The same video on a mobile is not going to be seen as many times as in a laptop, or as in a TV, for example. You should monitor many outcomes that are affected by the machine learning model, by the what's next. So, for example, how much time you're monitoring, you're watching it. You have to filter spam videos. Something that we've learned is that training goes extremely fast. But if we have in our pipeline a mechanism that detects spam videos, if that pipeline is broken, you might get that spam video into your training set. And at some point, you have to go back and eliminate those videos. You might want to deploy every certain hours or every days. And sometimes that doesn't happen with your code. Your code might be deployed every 2 weeks, for example. And we will see the importance of continuous training models.
All of the stuff Carlos just mentioned is the meat and potatoes of the SRE role. This is not the responsibility of the data scientists who are coming up with the models. They come up with the models, and then it's up to us, the SRE, to apply our best practices to making sure that these models form a healthy part of the production pipeline. So what we're going to do for the remainder of our talk is describe some of these best practices and the rationale behind them. And when you see this light bulb, that's our ding, aha moment where we had encountered something that we found to be a really good, really almost, dare I say, a best practice for ML in production services. And I want to emphasize that this draws on our experiences as well as the experiences of many of our colleagues. We had the great privilege of being able to collaborate with many teams across Google as we came up with these best practices.
So, okay, Google, what does a machine learning pipeline look like? What's machine learning like in production? So I'm just going. So the answer that we got from everybody is it's just another data pipeline. Don't worry, it's just another data pipeline. So we say, okay, this is what I believe is a theoretical machine learning pipeline. And by theoretical, I mean not empirical. So we got the impression that people spent an effort offline of building that model and then training, which is 10%. That means that you have production data. Remember, this is offline. People transform that data. There's a bunch of computation using special hardware resources, GPUs, TPUs. Then there is a validation phase, and when that validation phase happens and you're okay with the accuracy, you have what we call a trained model. That trained model is ready. We push it to production, we deploy it. And then most of the time what an SRE would be doing is having an effort of controlling the second phase, which is you have a user-facing request, you transform that data, you compute the prediction you serve. The prediction can be predicting an outcome or classifying it, and then you're doing that by using the model. However, this is already deprecated, okay? This is not reliable.
In order to make it reliable, we're going to apply some of the tenets of SRE to make things reliable, to make things reproducible, and to ensure that we have easy, good practices. And on this slide, you'll see the buckets that these practices break into. And I also want to emphasize that training, that is taking the data and putting it into the model, is an essential part of the SRE responsibility for an ML pipeline. And this is a theme that's going to recur through this talk. The training is absolutely a part of your overall production system. And in particular, the quality of the training will have significant effects on the quality of the service that you provide.
Training now has become part of your production pipeline. It's not anymore like coding, like debugging or testing. SREs are completely involved in this phase. And the input data to your models and the training pipeline cannot be stopped. And the reason that this cannot be stopped is because production changes fast, because data changes fast. And the way we see this is because models lose accuracy very, very fast. And you want an example about that? That was me maybe 3 months ago, maybe last week, maybe a little bit more, or maybe yesterday. I don't know, when I was so young, or when I was so sleepy. And our model has to detect that. So if I'm growing a beard every week and shaving it, that's going to be hard to detect, okay? In this graph, I'm basically showing you for a machine learning model the age. So the y-axis is basically showing the age of the model, and the x-axis is showing you time over 3 weeks. And what we're seeing here is basically one team pushing models continuously. For confidential reasons, I'm not going to tell you the y-axis, okay? But something that we learned here is that there are updates continuously. That the insight is you never stop training. Models need to evolve fast.
In the models that you're building and deploying, you want to make sure that the quality of the data that you're putting into these models is good quality data. And we asserted earlier that one of the myths around ML is that more data is better. And that it's generally true that more data is better. But if you're putting in a lot of repeated data, such as you're uploading, you have users uploading the same video multiple times into your YouTube ingestion pipeline, then that doesn't help the quality of the model that you build. So you want to filter out duplicate data. In addition, you may have, on this slide towards the bottom, you see that rows 3 and 5 are duplicates. A filtering technique will remove one of those rows, and you're left with a slightly leaner and still very efficient model. You also want to impute the data. That is, find places where the data is not uniform, where data might be missing fields, and add in nulls or estimated values. The first row here shows where there's a null placed for Carlos where we didn't have a particular value. And this comes into play when you are adding features to your ML model. So as models roll forwards and backwards, you may need to retrain and impute values. And this leads to a uniform set of input data that's clean and filtered and provides an efficient model in the training pipeline. And efficiency is especially important when you might be, over time, building up so much data. Some of YouTube's training models are over a terabyte in size, that you can't really load all of this into available memory. You might need to consider how to break it down, how to filter it more effectively, or even how to shard it. But the insight here is that you want to remove bad data, you want to remove duplicate data, and you want to add data imputation on all fields.
When we talk about training, we'll always mention data size. And in the training phase, we'll basically talk about the first part, which is basically your training. So you split your data set in, let's say, 70% of data that goes through that phase, and then 30% for validation. And for every single model that we've seen, there's no one fits all. Some data scientists will tell you 70-30, somebody will tell you 80-20. The most important part is that the data that you use for validation, your model should never have seen it for training. And do not confuse training and validation with qualification, which is an important phase that we will introduce later. The next thing is that we train at a scale. the input sets increases significantly. This is a very large data set. You're going to be training continuously in batch, and you're going to be trained on different input sets that come from different areas, for example, Asia and Europe. One of the very first questions I ask all those teams is like, okay, so for Asia, do you have a different model than you have for Europe? They'll say no. I say, why? And I would say, well, they speak different languages. They have different behavior, different cultures. No, that enriches a lot my model, because you might have users from Asia that have traveled to Europe. And the machine learning model, when you do the inference, when you do the prediction, will automatically detect that. Okay. The other thing is that you need a lot of compute resources. And since we need to continuously train, what we do is we take snapshots of our models. So if we're training for a week, we would be waiting 1 week until we can deploy that model. But if we have the snapshot of the model until Tuesday, we can only have to train from Tuesday to Wednesday, and that will be much faster. And indeed, if we have several models, what we can do is more parallelism and have different models that basically train from Tuesday to Wednesday and have different models as an output, and then see which one of them behaves better. Because there's going to be cases where your data scientist says, have different types of models, and depending on the next phase, decide which one you deploy. Okay, summarizing training and data quality. Features, which are every single field that you saw on that table, those are details that literally the model will absorb. So you might have strings there that might have capital letters or not capital letters. You have to be coherent on that, because all of those details will become numeric values, binary values that your model will take into account. And when we talk about data quality, we summarize it in like correctness and completeness. For correctness, we want data imputation and data validation. We talk about snapshots because we want to be able to resume and roll back the training. We talk about bias. We want to monitor data ratios. Bias and data ratios go together. We want to make sure that if we are getting 1 billion input sets from Asia, we always hit the same ratio when compared to Europe. Because if we unbalance those, we're going to get, and our model is going to behave unexpectedly. So if at some point one of your input pipelines from one continent breaks, you need to take that into account. You might want to stop the training, because otherwise you're biasing to the decision based on the information that you get from your input set from Europe. The same day for a weekday. If you think that you can train a model from Monday, Tuesday, and Wednesday, and use different ones, experience from other users tells us that's not correct. Just train the model with all the days, because the model will basically acquire that knowledge. Because you're probably going to have a feature that is going to be what day of the week it is. Anomalies. Be careful if you're training on Super Bowl. Be careful if you're using New Year's Eve data. That might introduce, again, bias. And automation. Today, you have input data from the past. But at some point, technology will allow you to give more metadata to that input set. So you might want to have automation so that you can go back to that input sets and basically upgrade it, give more metadata. And that has to be done with automation. Okay, so before we thought the machine learning Bible was just what do we have on the top. What happens when we use the experience from all those teams? How do we transform that pipeline? So we basically add a phase of data quality. In basically the production data that we have goes through a data imputation, we do some filtering, and since we appear to have snapshots, what we do is we have parallel trainings that will have parallel validations and will give us different training models. We don't have to decide yet which ones of them we're going to use, but we're going to have more outputs in terms of which models do we want to deploy later.
Another key part of being an SRE is understanding the resources, the physical resources as well as the software resources that your system will use. And efficiency in training has become so important that many companies, including Microsoft and Google, are building and deploying their own hardware accelerators. This has a profound effect on the behavior of your system and on its resource consumption. So as you, as an SRE, are figuring out how to fit different parts of your model training into your production ecosystem, consider that within the last few months, what previously took an hour's worth of training time across 32 GPUs might now take only a few hours on a fraction of a TPU pod. And because Google produces new TPU versions every year, this will continue to change, and you'll need to be able to quantify and assess your pipeline in order to account for the resources that your system will take. And the cost of training, or training is the more resource-intensive phase of the machine learning pipeline that Carlos was describing. For example, YouTube will decode and examine each of the videos as part of its training pipeline. It will extract labels, add these labels into the model, and these become features that are then deployed into production. As the new hardware becomes available, we might train YouTube to identify all the different breeds of cats and the models of pianos that are in these uploaded videos and add those labels. However, if at some point we roll back to a previous model, then we may need to retrain in order to re-extract those labels. These are very processor-intensive phases. And we switch to a very disjoint environment, which is the serving part of the pipeline, where you are now concerned with very low latency user-facing requests. And here, this is where resource limits again become very important. You want to be sure that there isn't any part of your serving system that's starved for resources because you haven't provided proper isolation. That is, you want to make sure that the training jobs, or the training portion of the pipeline, has only the resources that it needs and can't intrude upon the serving part of the pipeline. And one of the shortcomings of much of the existing GPU hardware is that there aren't reliable multi-tenant approaches. That is, there isn't a good way to provide isolation for multiple processes to share the same GPU. There are projects underway that will make this possible, but they're not yet as reliable as they might be.
So now let's introduce another phase, which is qualification. What we understand for model qualification is we want to make sure that the model is ready for production. And the way we do this is by using new input data that might be data from production or from the previous day, into a model that is already trained. We only want models that are tested to go to production. That's the key inside. And in order to go to production, we want them to be qualified with the same binary as in production. We've seen some companies that instead of doing that, what they have is an A/B testing a scenario, and they basically will have a knob. They have an old model that is in production, and the new model is basically just being tested by giving them a portion of the traffic. In this slide, I'm basically showing something that we found through most of the teams, which is you really need canary. Even if you're using a very small percentage of your production as the input to the canary, you will see that it behaves very similar to the model that you have in production. And at the same time, you're validating that that model is compatible with the binaries that you have in production. A way of guaranteeing that is basically by signing the model. And signing the model is nothing else than giving some metadata that describes what is the input set, what is the output that you're expecting, and the compatibility with the binary. And the key inside here is only allow signed models to go to production. Because we've all been on call. We've always had somebody sitting next to us saying, push it to production. We have to stop the bleeding. Only do it if the model is signed.
The importance of having signed models, that is a guaranteed way that you can identify models that are legitimately good, both the current generation and previous generations, becomes a little more subtle when you consider that the models, as they evolve over time, may add features. They may have different labels than a previous generation of model. This is where data imputation again becomes important, that you might need to retrain a previously signed model in order to impute the data so that you can roll back to it and push it back out to production. Additionally, the notion of defense in depth comes into play here. If you don't have a way of rolling back, if you can't afford to, for whatever reason, to roll back to a previously signed model, or you don't have a previously signed model, then you may lose that user-facing feature that your ML pipeline was building up. In that case, you may want to fall back to a heuristics-based feature, something that uses more static data and doesn't have any ML as part of as part of that feature. And this is something that many groups across Google do have, which is they fall back to a heuristics-based model. This happens at YouTube and some DeepMind systems. And one other key thing that we found was that we need to actively deprecate old models. That is, if we know that even though we have an old and signed model, we may need to mark it as deprecated and know that our system can't use it. And this then also suggests that we have a good understanding of the interaction between the model, the configuration, and the code that is using that model. Understanding this as part of a release practice is described in the release engineering chapter of the SRE book. But what's different about ML is that some of the model changes are dependent on APIs. And you may have a reliance on a framework such as TensorFlow. Their API may change in ways that are subtle and will affect your model. So then you need to examine your model against the data, against the expected results for your end users, as well as the interaction with the API. And time and again, we heard people say that they had developed a model and tested it for production, but they hadn't tested it against different API versions. In addition, you can't add a new feature to an old model. That is to say that once you've added the cat and piano information to a model and push that to production, then you realize you need to roll that back. You'd have to retrain that model in order to you'd need to retrain an old model in order to deploy it and make it available to production again. And this is something that you need to be aware of as you're considering the effects of rolling forwards and backwards. We also found that rollbacks have subtleties which often required human judgment. So if you're asking yourself during a war room or during a crisis, does your rollback involve human judgment? That is, an engineer standing by to say, yes, this is the right model to roll back to and I can sign off on it? Well, what do we say to that, Carlos?
No bueno.
And one group that we spoke with, which is a critical revenue producing group within Google, observed that a better way for automating rollbacks, that is making them fast, is a project that is much needed within ML engineering.
Okay, Google. So tell me now, what does a machine learning pipeline really look like? So what we've seen through the presentation is that we need to improve the training phase by adding data quality, by having several models being trained. And when we have several models being trained, we basically have checkpoints or snapshots. Train models that we can use later in a new phase that is called qualification. Qualification gets live data or new data. We use those trained models and we do predictions with the same binary that is running in production. And then we monitor those to basically get a champion model, which is basically a model that is ready to go to production. And we're basically having monitoring over models that might not be used in production. So we're introducing something new here, which is we're monitoring something that for us in the past would be development or testing. And we have alerts for that. Because if we have models that are not going through the qualification, if we are not able to get a champion model on time, we're basically aging the model that we have in production. So at some point, the accuracy of our predictions is going to go down. The application feature is not going to be so accurate. In addition to this, when we go to live serving, we make sure that we have data imputation, and we only use a champion model, which is we only use a model that had a signature.
I want to draw your attention here to the unassuming black box that says alerts. And The type of monitoring and alerting that we found was lacking in many of the ML pipelines we looked at. It was significant. That is, ML really requires context-based alerting. You want an understanding and a knowledge of what your end users, whether those are people or you're providing an API endpoint, what they're expecting, and you want to be able to react to that very specifically. And of course, you want much of the sort of alerting around latency and performance, but you want to monitor latency for how long your training phase takes, as well as the latency for end user serving. And when you're monitoring that end user serving latency, you definitely need to account for API overhead, as well as any RPC framework. And we found that many groups weren't doing that. And so they missed any variation in that baseline and weren't able to tease apart the performance of the API from the performance of their pipeline. And in addition, you want to monitor prediction latency. That is, how long does it take to deliver the inferences to your end users? What I really want to talk about is context-based alerting. And this shows a simplified view of a revenue-producing service at Google. And there was a model change, which was expected to increase the number of clicks on the service and also produce a corresponding change, positive change in revenue, and it did. However, what we hadn't accounted for was that different demographics might react differently to the new model. And here we see that one demographic was much more enthusiastic about clicking through on the inferences produced by the new model, and another was not. And so there was a degraded performance for one group, but a significantly improved performance for another, because we didn't understand that there were different audiences. We didn't have this contextual alerting, and so we missed out on an opportunity. We also didn't effectively meet the expectations of our users. This did lead to a loss in revenue, but more significantly, it gave us the understanding that we need context-based alerting. So the insight is that your alerting must be domain-specific. It must have an understanding of what the end-user interaction is.
Okay, and to conclude, let's go to also an important topic, which is privacy and ethics. And basically, when we talk about privacy, we're talking about user data. Whenever you're using individual data, make sure you anonymize your data. Make sure that users are that you cannot identify users by the prediction outcome of the model. We've seen teams that they will have even a cascading, like a pipeline of models. So make sure that your models cannot identify the user at the end. And make sure about that by anonymizing the data. You need to be able to delete user data. Remember GDPR. So you have to have automation that basically is able to delete individual data and retrain those models. Ensure your model doesn't have any user data. And in the case that it has it, make sure that you know how much time is it going to take from deletion to training. Because you might have to delete completely the snapshot and start from the very beginning. And if you are talking about a team like YouTube, it's basically massive the amount of information that they have for training the What's Next model.
And ethics in ML and ethics in algorithmic-based software is, without question, a big elephant in the room. And I need to take a deep breath because it's a big topic. We have a very small amount to say about it. SRE have a distinct responsibility to participate in and be responsible for the quality of the predictions that we're providing, as well as the quality of the data that goes into this pipeline. And SRE have the power to make changes here, and it's important that you, as SRE, that we all participate in any ML-based pipelines that we build. And there's also a clear and growing sentiment for independent oversight. That is something that spans or is bigger than any company. And this sort of oversight might take the form of a third party that offers guidelines and then calls on companies to not only abide by these guidelines, but provide transparency that they are following these guidelines, that they have groups within the company who can examine the predictions from models as well as the type of training data that's put into these models, make recommendations to the product groups at those companies, and then ensure that those recommendations are followed up. That is, that they don't just go into dev null. This is significant as ML becomes an increasing part of apps and websites that we use every day. It becomes a part of systems that we don't interact with directly, but do have an effect on our daily lives. And I don't want to give you the impression that ML is new. ML has been a part of software for generations. But the increasing availability of compute resources means that it's easier for ML to be brought into many products. And the responsibility that we have to do that in an ethical and fair way is something that we need to consider.
Let's finish. We'll be talking about training continuously. We'll be talking about filtering, data imputation, stamping in models, deprecating all models, and user domain-specific alerts. But let's be more precise on the insights that we believe we got from all those teams. Migration from previous regression heuristics is complicated. There's teams that get machine learning and then they get new application features. Those teams usually do not have a rollback mechanism when the machine learning model is not there. So you have to be ready to tell your users, I am sorry, but that feature is not available at the moment. Pushing a new model is not just a simple code change. There is many more verification steps that we need to do. Training is part of your production, and training needs to happen frequently. You need to have batch continuously training models. And the demand of resources grows significantly in this phase, much faster in the training phase than in production. And you need to monitor serving latency. Most of the problems that we found when reading through postmortems, it was basically data changes. It was basically the lack of monitoring for those data changes. For example, when we were removing spam content from YouTube, when the spam pipeline was not working, some of the teams, instead of going through their model and deleting that data, what they would do is they would introduce new fake negative data that would basically balance that information, just because training the whole model would take too much time. The relevance of canary, and the relevance of canary happens by running the model through a qualification phase, signing it, and using the portion of your production live data to test that model.
No survey talk at SREcon would be complete without some prognostication about where we're going with ML in the coming years. And since we wrote this slide, already some of these things have become more prominent. But I do see, or we do see, that there is increasing availability of open source data sets. And these are data sets that have been fed from vetted and unbiased sources. They're filtered, and they're data sets that you can use to train your own models. We also expect that there will be increased techniques for sharding models and possibly domain-aware routing between different models, so that as models grow in size or as models grow in quality, applications will choose which part of a model or which version of a model to send a particular request to in order to produce optimal results for the end user. We also see and are already seeing the growth of models as a service, where you may not even build an ML model yourself, but you'll rely on a cloud provider to handle requests on your behalf, or you'll send them data as part of your application, and they return the labels or inferences to you, and then you act on those within your own application. And this talk would not have been possible without the collaboration and great conversations we had with many of our colleagues across various groups at Alphabet, including Google. Within Google, there are several groups, DeepMind and YouTube, and to our colleagues at several other companies, including Clarify and ThoughtWorks.
Thank you.